right? I guess people sort of assuming that because we are in midterm that we wouldn't have a class this morning, but um, what we're doing today is that there are sort of three lectures that I have on the Z transform. Almost all of it is stuff that was done. It's just repeated here, but is almost entirely stuff that was done when we did the Z transform in Signals and Systems some time ago. So what I've done is that because a lot of it is just revision and it's things that you can go through for yourself, I have extracted from those three lectures one sort of summary lecture, which is what we're going through today, right? The three lectures are available, and I'll also put up the summary lecture. Plus, you will have the recording of this to have a look at and have a listen to. The idea behind it is because the next half of the course, we're going to deal with filter design and sort of filter manipulation. And to do that, you're working almost entirely in the Z domain, sort of like what when you did your control systems, you're working in the S domain, and the manipulations have to just to refresh our mind about the type of manipulations and so on. All right. If you have questions, as usual, you have to sort of prompt me and ask. I can't see the chat while I'm watching the screen. All right. Okay. So thanks for attending, and let's get going here. Right. So just a little bit of sort of context here is that you remember that the whole idea behind why we had to find a tool like the Laplace transform was because when you're dealing with continuous time systems, invariably the continuous time system is described by a differential equation. And as simple as a circuit that has a capacitance in it, for instance, right? From the time you put a capacitance or capacitor into a circuit, a simple RC circuit now, because of the behavior of the capacitor, you now need a differential equation to describe the currents or the voltage in a simple RC network. So to solve that, no, there were many ways that you could solve a differential equation. If it's simple enough, you simply integrate. But then what we saw is that okay, that doesn't work all the time, or it's a little bit difficult to do. So we were introduced to another tool, which was the Laplace transform, and basically what the Laplace transform does is that it takes you from a place where you have to solve the equations, the differential equations, and so on by using integral and differential calculus to a place where you can solve the equation using simple algebra. So you solve an equation or simultaneous equations, and then once you have the answer now, you take the transform back to bring you back to the real-time world that we are in. And this was covered, of course, we did this. You had a whole course on the Laplace transform. We did it in context specifically for addressing how signals and systems work. And then your controls course, of course, delved very deeply into that. I'm showing you now, based on the type of transfer functions, which were all described in the Laplace transform domain or the S domain, that you could do a number of things there and predict how systems performed in response to certain signals going into them. So um, remember, too, is that the Laplace transform is a function of this variable S. S is actually a complex number. It has a real and an imaginary part. The real part, or sigma, the standard notation is to let S equal to sigma plus j omega. The sigma part is what controlled whether the particular expression in terms of S would either decay or grow in amplitude. And the imaginary part determined, this part here, determined your signal behavior with respect to your expressions behavior in terms of frequency. And we made quite a bit of use of that when we were doing things like the Bode plots and addressing things like the Fourier transform and so on, right? And it allowed you once you solve the solution, once you solve the system, you now were able to translate it back into real components. Okay, and we saw that. We saw integrators you could make with op amps, and resistors, capacitors, and so on. Basically, an answer that is a filter. It has an amplitude response, it has a phase response, and it has some transient and steady state response. Okay? In the case of the discrete time system, the answers that you would get, as we saw when you input into a discrete time system, is a set of numbers coming out or a sequence of values. Okay? The thing about it is that, we mentioned this before, is that the Laplace transform doesn't work well with sample signals. And why, we'll just recall briefly what happens. If you consider some signal cosine omega k t, if you take the Laplace transform of it, then you get s over s squared plus omega k squared. And I can factorize that, the denominator into two parts, s plus j omega k and an s minus j omega k. In other words, the cosine, the Laplace transform of the cosine omega t is giving me two poles, two complex conjugate poles, right? One at s plus j omega and one at s minus j omega. Okay? So each omega k, each one of these gives me a pair of poles, one at plus j omega k, one at minus j omega k. Remember, when you sample, whenever you take a signal and you sample it, and we did that early on, you now get a series. You have the original signal components, which in this case would be omega s, but you get the signal frequency components now being replicated at infinite numbers of omega s and omega k. So you remember, if the original, if I were to draw it here, you're right. So if cosine omega had, right, omega k, this was the original spectrum here. It should be a subscript, but anyway, when you sample it, the spectrum now gives you, at each omega s, you get omega s plus omega k, and omega s, you have omega s, so this will be omega s plus omega k, and this will be omega s minus omega k. Similarly, you will have on this side at minus omega s, and then at 2 omega s, at 3 omega s, all the way up from up to infinity, and it goes plus or minus infinity on either side. So in other words, once you sample a signal, and we saw why it happens, you create, by sampling now in the frequency domain, you start to create signals, replications of the signals. So that if you now take the Laplace transform of a sampled signal, what you're going to have now is that each of those replicants, so the omega k t, the cosine omega kt will give you something, but the one at omega s plus omega kt will give you another pair of poles, and so you keep going on. So the Laplace transform of a sample signal now is going to have an infinite number of poles in the S-plane. That's not going to help us. All right? Everybody understand? You're clear? It makes sense. You remember from what we did with the sampling and spectrum replication. Yeah? You have to let me know.
Yes,
Right. So once we're dealing with discrete time systems now, we're dealing with sample data. The sample data cannot be used in the Laplace transform because it's going to give us an infinite number of poles and zeros. So we need another tool. What we require is some tool that maps, if you have all of these infinite poles and zeros, that you somehow map it onto a finite set. And this is where the Z transform came in. This is all part of complex number theory, and it's not, we never did the derivation here, and it's a pretty intense, it's almost a part of a course on its own, how this came about. But essentially, by making a substitution equal to S and capital T, which is a sampling period, if you substitute this into the Laplace transform, right? So in other words, you replace the Laplace transform S by a variable e to the S capital T, and you can see already that is not a particularly easy thing to do anyway. But by doing that now, and with a lot of complex number manipulation, there's a new transform that comes out of that called the Z transform. And the Z transform basically works on discrete signals. So if I have a discrete signal xkt, which is a signal sampled at multiples of the interval t, right? So it will be at t, 0, t, 2t, 3t, etc. Then we define the Z transform as you take the xkt multiplied by z to the minus k, and then you summing from minus infinity to infinity. Remember the Laplace transform. The Laplace transform started out from minus infinity to infinity, but because we were dealing specifically with causal signals and so on, we dropped the lower limit from minus infinity down to 0. And then mathematically, because I don't know if you remember me telling you this, you can't really integrate. One of the things that you learn in AdMaths, and you still do, but it's technically not correct. If I tell you to integrate something between -3 and 4, what we usually do, if I have some fx in here, what I usually do is to integrate fx and then substitute x equal to 4 and x equal to -3, and you work it out and so on. Technically, you can't do that because you can't integrate and substitute at the same the limit that is changing, because remember fx is a time varying thing. So what we did is that really and truly what you're supposed to substitute here is a little before -3 and a little after +4. So here mathematically we tell it, we put 0 minus. So the signal has finished changing by the time we reach 0. All right, you can't integrate and at the same time the signal is changing. Right, we kind of ignore that, but that's where we got the minus sign from the Laplace transform from. Right, so the Laplace transform worked on causal signals, so the lower limit changed from minus infinity to 0. We saw that sampled signals may or may not be causal. So the data could actually we could have stored information, which is really before t equal to 0. So this is why we have to maintain the k equal to minus infinity, or start from before 0 and go to way after 0 and so on. Right? That was a two-sided transform. And of course, if you're dealing with a one-sided transform, which is where you know that the signals, the data that you have for xkt starts at 0, then the summation will start at 0. All right, so this is the one-sided version. So one-sided or two-sided, like the Laplace transform, just depends on what you're doing with that lower limit there. Fair enough? Right. So it is a complex number quantity, and it is a power series in, well, this variable z, or z minus z to the power minus m. Okay, and it is plotted in a space called the z plane, just like how you plotted the Laplace transform in a place called the s plane. Right. So if you expanded it, the Z transform of a sequence of numbers xkt will be the one-sided transform. Of course, let's assume that it is a causal sequence, will be x0, z0, xt, for the next value, or the next sample, z minus 1, x2, t, the z minus 2, and so on. So if the values were like 1, 2, and 3, if this was my xkt here, then the z transform of that will be x naught, which is 1, z to the power naught, plus x2, then the next value, right, which is 2z minus 1, and the next value, 3z minus 2. Of course, z to the naught is 1, so this will be 1 plus 2z minus 1 plus 3z minus 2. Right? So for a fixed size sequence here, you could literally write out the Z transform. It's just each consecutive element by the appropriate value in of z, z to the minus whatever that particular index is. So very straightforward, right? And of course, we saw that, don't forget, z minus 1 is 1 over z. Z to the power minus 2 is 1 over z. We prefer it in this form, and you will see why a little bit later on. That is the form that is used predominantly in electrical engineering, specifically in signal processing, and also in things like discrete controls as well. The math books or the mathematicians tend to prefer this, right? Because I guess the negative indices kind of create somewhat of an issue for them, all right? But it's easy to go from one to the other if for some reason you need to. And as we will see later on when we're doing some filter designs and so on, we have to go back and forth between the positive and the negative indices, all right? So let's look at a little bit of the relationship now between the Z transform and the Laplace transform. Remember, S is sigma plus j omega, right? And Z is e to the S capital T. So let's consider the particular case where sigma is zero valued, right? So S is just simply plus or minus j omega. So we're going inside of there, and if I tell you, if I give you a number e to the plus or minus j omega, that now is really, the magnitude of that is 1, and the angle varies as plus or minus omega t. We kind of saw that just a couple of weeks ago when we were doing the twiddle factors for the FFT. So you can represent Z as a phasor whose magnitude is 1 and whose angle varies by whatever omega t happens to be. And you could evaluate this, in this case, let's just see a little calculation here. And this is to make the comparison between the Laplace domain and the Z domain. If I take 8 values, so I divide omega up into 8 pi omega s over 8, 4, so on and so on. The equivalent value of Z are these going along here. So one angle, and I'm putting it in degrees here, 1 at 0, 1 at 45, magnitude 1 at 90, and so on. So it is a rotating phasor, except that for positive values of omega, of course, we're going anti-clockwise. The twiddle factor went, we're going anti-clockwise. The twiddle factor went clockwise. So if I were to plot this, remember, S is equal to j omega. If I map this, S equal to j omega is going up and down this axis here. Right? So S equal to j omega basically is going up and down that line. That now, if I map that, remember the first point here. So this is, if I go back to my table here briefly, this is the point 0 here. Right? And notice that the point 0 is mapping to a point 1 angle 0. And then as I go up this axis here, as I go up that axis, I start to go around the unit circle. Right? So I actually go around the unit circle this way. So as I go, the next step was 1 angle 45. Remember that was the other one, then 90, then 135, then 180, and so we're going on. Right? So in other words, the j omega axis of the S-plane maps to the unit circle, a circle of radius 1 in the Z-plane. Everybody following that? Yeah?
Yes.
Right. So the imaginary j omega axis maps onto the unit circle. And then now, if we consider now putting some value now to sigma, if we begin on the left half of the S-plane, so we now have sigma is minus. So minus sigma plus j omega t. I could sort of bring out that again. So this is e to the minus sigma t multiplied by e to the plus or minus j omega t. So this now, we already know that this is one by this is the unit circle here. So that since sigma is negative, e to the minus sigma t is a decreasing number, is less than 1, so that this particular, the magnitude of z is going to be less than 1. In other words, inside of the unit circle. So if I were to look at that now, therefore, once I have sigma negative, which is here, all of this is going to map any value of sigma that is negative is going to map inside of the unit circle. And remember that was that now was the significance of, first off, sigma lying negative or in the left-hand plane. Remember, that is where, when we were talking about a Laplace transform, that you talk about what do you call it, stable systems. So stable systems in the Laplace transform domain, if you take the sample of that appropriately and you calculate the Z transform of it, it maps inside the Z plane, inside the unit circle. All right. So a system that is stable will therefore have to have Z-plane values inside of the unit circle. The left-hand side maps inside of the unit circle. And in fact, when you're doing discrete time control systems, one approach of it is that if you have, if you take a system that you have designed, a continuous time system that you've designed, and it is stable, meaning that the poles are on the left-hand side, if you carefully sample that signal, and then take the Z transform of it, then the poles are going to be inside of the circle and the system is going to be stable. All right. So you have to do it carefully. Of course, we have the sampling criteria that we spoke about before. And there are a couple of other things that we do. If you have done advanced controls or you're doing it, you would have met that already, or you may have, or you probably will be coming across if you're doing it next time. Right. So what about, you remember one of the things we said is that the S-plane, when you sample, you get these multiple repetitions of poles at omega s, which is why the Laplace transform couldn't work. So what about the Z domain version of that? Well, we just have to look at the behavior of Z in relation to S. So Z1 is e to the minus sigma sigma plus j omega. If I have a sample, so let's just take it sampling at plus omega s. So omega now is omega plus omega s. I have to expand that a little bit. Right? Notice here that omega plus omega st is omega t. And remember, omega s is 2 pi over t. This is sampling frequency here. The t's cancel so that you get that this now is just the same omega t that you had before plus 2 pi. 2 pi, remember, if you're plotting on a circle, 2 pi means that you have gone around the circle and you're back where you started. So in other words, as far as our plot of e to the j omega plus omega s capital T is, those 2 points, Z and Z1, will be the same point. You start right here, right? So every plus or minus omega s that you have, in other words, all of those 1,000,001 replicants that you had in the S-plane, all of them going to map to the same point here. So every particular value of omega s that you have will map onto a single point in the Z-plane. So we've solved that particular issue in that the Z transform will now take the infinite set of poles that we got in the S-plane and map it to a finite set of points in the Z-plane. So it has solved that particular problem for us. Yeah? Make sense?
Yes, sir.
right? Some of the properties quickly, right? They, well, is causal is a complex quantity. Z is a power series in, XZ is a power series in Z. So if it's a power series, remember we just did one, just an example with one, if X was 1, 2, and 3. In that case, if this was XK, XZ was just simply 1 plus 2Z minus 1 plus 3Z minus 2. This is nice, this ends. But what happens occasionally is that you get, if you're not dealing with this, if you're dealing with an expression for Z, for XK, sorry, XZ could go on and on. This now, remember this is a power series. If the power series does not end, in other words, if there's not some sum, you remember when we did it, there was not some a value of a sum to infinity, right? From your power series and so on. If you can't find a sum to infinity for XZ, then the Z transform doesn't exist for that particular, whatever that particular XK is that you're trying to find. And you have to be careful with that, all right? We didn't do, it's not a math course to give you examples to say, well, if this has a sum to infinity or not. But just like with the Laplace transform and with the Fourier transform, in both cases, one of the conditions that we had was that the integral, you could actually find an integral. We just assume that if I give you some mathematical expression and I integrate it, that the integral really exists. Right? From a mathematical point of view, you have to prove that it really exists, right? And take limits and all that kind of thing. Luckily for us, all of the sort of signals and so on that we deal with have already been evaluated, and we know that the particular integral exists. Same thing for the Z transform. So most of the things that we will deal with have a value that sums to infinity. Right? In other words, that power series converges at some point in time. Okay, so just for noting, but you will see it if ever you're doing other work, postgraduate work or graduate studies somewhere and so on, and you're coming up with something new. One of the things that you always have to make sure is that if you have something, a new mathematical expression or something that describes something, right, that the math of it, the maths of it actually does exist. Okay, just to keep in the back of your mind. Right. So let's see. We've just seen in the last few slides the relationship between the S or the Laplace transform and the Z transform. Let's see now what is the relationship between the Fourier transform and the Z transform. Early on, we had when we started to look at the Fourier transform, we saw that the discrete time Fourier transform of a sequence was given by this expression, right? E to the same xn, e to the minus jn omega. And remember omega, this here omega was omega ts, okay? Or 2 pi f over fs. All right, you're going to meet that quite a bit in the next few weeks as we go through some filter designs and so on. The same sequence xn, the Z transform of it is given by the expression shown below here. So at what point, when is x omega equal to xz? What will make those two equal? If I give you those two expressions there, or those two equations, sorry, the one above, the one in green and the one in yellow, and I ask you, well, what will make the two of them equal? What will make x omega equal to xz?
When z is equal to e to the j omega.
Right. So basically, if you For these two to be equal, this thing here and this thing here have to be equal, right? So z to the minus n has to be equal to e to the minus j n omega. All right? So at that, if you look at that, you see that for x omega to be equal to xz, z has to be equal to a e to the j omega. Next question, where is z equal to e to the j omega? Remember, e to the j omega is simply a circle of radius 1. In other words, z equal e to the j omega is on the unit circle. So the dtft, let me just backtrack a little bit. The s-plane and the z-plane, the s-plane, the j omega axis mapped onto the unit circle, right? So that was the relationship between the s or the Laplace transform and the z transform. In this case now, the dtft maps directly onto the unit circle. So in other words, just like how you remember we were when we were doing the continuous time Fourier transform, we said that if I wanted to find a Fourier transform of some signal, then what I could do is to take the Laplace transform and let s equal to j omega. There were some exceptions, but we're seeing why now. S equal to j omega is this axis, which is the frequency axis of the S-plane. So now, when we're dealing with the dtft now, the dtft, which is the discrete time now, we see that once you have the dtft, if you make the substitution sz equal to e to the j omega, now what you're going to do in the z-plane, you're going around the unit circle, and this is where you get the answer for the dtft. Right, so just like with the relationship with the Laplace transform, up and down the S-plane gave you the continuous time Fourier transform. Around the unit circle in the Z transform gives you the dtft. All right? So the dtft is therefore the equivalent of the Z transform evaluated on the unit circle. Now what that means is that if I have some expression, right? And this is the unit circle here, okay? And the region of convergence of that expression does not include that unit circle, then whatever sequence it is will not have a dtft. In other words, the answer will not converge. Just like if I were to give you an expression in S, right? Some expression in S, and that expression does not include the j omega axis. So let's say the expression is all in a range like here. This is the j omega axis here, and some expression in S, and the only place that the expression exists is in some zone that does not include the j omega axis. This expression does not have a continuous time Fourier transform, CTFT, right? So same thing here. If I give you some Z transform and the Z transform region of convergence. So let's say, let me just change the color here. So let's say the region of convergence for this particular thing is in a zone outside, outside of the unit circle. It starts at some point where this radius is bigger than 1 and continues outwards. This does not have a discrete time Fourier transform, okay? Just to put things in context, why you need to, why when you have sequences or you have expressions, that you have to make sure that they're in fact converging in a particular region, okay? Just to remember. So, for instance, just let me clear some of that a little bit. So if you have something like some sequence minus alpha k u minus n minus 1, mathematically you could get a Z transform equal to Z over Z minus alpha. The region of convergence for that has to be that Z has to be, mod Z has to be less than alpha, right? So this will only converge if mod Z is less than alpha. If alpha is less than 1, then this particular expression will not include the unit circle, and it will not converge, okay? Just to keep, well, I mean, just something to keep in the background there. Everybody following so far? We all right,
Yes,
right?
sir.
Good, and it's something that you, I mean, I have 3 lectures on this for you to review, plus this one. So the Z transform now, we could express it as a ratio of polynomials, right? Polynomials in Z, just like we could in the Laplace domain, you could express it as a ratio of polynomials in S. So you could also, of course, factorize the polynomials. So you could have them in terms of either this form, or you could factorize them and have them in terms of the poles and the zeros. Okay, just like we could do in the continuous time domain. Yeah. And then, of course, one of the things about transforms is that if you want to get a if you take a transform to go to some domain to help you out, you have to be able to come back. How do you get the inverse transform? Just like you did with the Laplace transform. So you take the transfer function itself, you try to get the transfer function into partial fractions, and then you, after you solve the partial fractions now, you go to look up tables and you get the answer. Same thing with the Z transform. All right, so the inverse transform, in the case of the Z transform, you had 3 ways of doing it. One was long division, one was complex integration, and the other one was partial fractions and tables. The long division approach is unique to the Z transform. Right? This one is unique to the Z transform. Right? The Laplace transform doesn't work. It doesn't have a corresponding way of doing it. Complex integration actually is the way that if I give you a very involved transform to find the inverse, that is actually how we have to do it. And that is how some of the more complicated inverse Laplace transforms have been done. And then partial fractions and tables, which is the one that invariably for our work in undergraduate work and so on, we tend to use. All right. So as in the case of long division, then okay, and just as a backtrack, notice that I have this this particular expression in terms of positive indices. You can convert it from positive indices to negative indices just by simply multiplying this by Z minus 1 over Z minus 1, right? Or Z to the highest power here. So if I were to, this is Z cubed, so if I multiply this expression through by Z to the minus 3 over Z to the minus 3, which is 1, right? It will convert this from the positive index form to the negative index form. And you remember we did work like that already. All right. So the 3 techniques, just quickly, the long division. If you want to find out the first few terms of the response of a transfer function, a discrete time transfer function, then this particular approach where you divide the numerator by the denominator quickly gives you what the first couple of values looks like. So you divide, of course, the thing, you must get it in this order. You must put the transfer function in the form where you have increasing powers of z minus 1. Once you do that, you divide the numerator by the denominator, and that's a normal long division, and you get this now as a divided answer. And of course, there would be something for z minus 3 and something for z minus 4, and so you keep going on. All right, but we're just looking at the first couple of terms. And once you have it in this form, getting the the inverse transform of it is as simple as reading all the values here. So the first value is 1.4, the next value of y and t is simply reading off the values here. So the y and t, right? The first value would be 1.4, the second value 0.94, the next value 1.1, and so on. Why is this important? It may be that you have some discrete time system. Let's say you're working with a system and you have a processor on it that is working with 3 volts. So you do something and the transfer function involving the whole system now gives you that expression. This is the transfer function here, right, that you have here. The first couple of values when you activate the system now, for this case, let's say is going to be 1.4 volts, 0.9 volts, that is it, 1.12, which is good, which is less than 3 volts. If for argument's sake, though, you were doing something and the first value here was 6.7, the second one was -5, and so on, immediately you realize, wait a minute, something going wrong here, right? I am limited to, let's say, 0 to 3. The values here are way outside of that range. Therefore, y and t is wrong. So therefore, yz has a problem with it and I have to go back to it. That's the beauty about the long division approach. It immediately gives you an idea what the first couple of values coming out of the system is going to look like. You remember, again, a discrete time system is xn. You go into some hn, okay? And coming out of that, you have yn or ynt, okay? So if you put in a set of numbers here, or like a unit step into the transfer function, and you get this coming out, and the system's supposed to work with 3 volts, that's fine. If you get 6 point something and -5 point something, then there's something wrong with hn, which means that there's something wrong with hz, and you're going to have to go back to it. Yeah? Make sense?
Yes, sir.
All right. Comment, right? It gives us the first sequence of values and so on. What happens, like in this particular example, if you keep dividing this, if I keep dividing the numerator by the denominator, this particular what do you call it, transfer function will keep giving me values all the time. In other words, it has something called an infinite response. There are others where after I keep dividing and so on, it will end after some finite number of values. That is called a finite response. That now is good. You could program that directly into a computer because each value that you get, you remember, is storage. So finite depends really on how much storage you have, how many numbers you can store on, that kind of thing. So if it keeps generating numbers, it means you will have to keep finding space for it. And that's going to create a problem. We will see how to handle that in a few weeks' time. But most things, if the thing has a finite response, it's easy to program just by entering the numbers in a computer, in an algorithm of some sort. All right. The next technique, of course, to find the inverse transform is to do complex integration. We're not going to do that. This is something called a contour integral and so on, and you have to do some fancy maths to get it done. But basically, if you have a very complicated, what do you call it, expression that you can't find, or you can't simplify into partial fractions in any form or fashion, then the only way to do it is to do the hard way, which is to do the contour integral and so on. all right? Not part of our menu. And of course, the last thing, like we did for the Laplace transform, and this is what I guess most undergraduate and even graduate engineers prefer, is to use partial fractions. So you take the Z transform expression, you break it up into partial fractions, and then you go to a table that somebody did for you, and you try to match the partial fractions to the inverse. The problem, of course, is if you can't find that. Luckily for us, and I don't know if any of you all have ever gone into the library and looked up, sort of pulled out a math book with transforms or anything. So they are huge books. So people have come up with Fourier, Laplace, and Z transforms, and the books run into the hundreds of pages, right? So you could always, with a little bit of digging around, you could almost always find an inverse transform or a forward transform to some kind of expression, because people have done it. It's been around so long that instead of you having to do it from scratch, you could go and find the answer in a book. Some of the information is online, but you have to be careful when people translate things or they type over things for online. Sometimes they make an error. So it's always good to sort of check a hard copy version when you want. This now gives us a closed form sequence. So unlike the other one, the division is giving you numbers. This one gives you an expression in terms of n, so you just have to put in whatever value of n you want, and you get the answer coming out. So quick review. Of course, like every time we've done this before, to do an inverse partial, to do a partial fractions, first off, the function that you're trying must be strictly proper. So that is that the order of the numerator must be less than the order of the denominator. If not, you have to do at least one division first to get a proper polynomial. All right. So if you have z to the power minus 2 on top and z to the power minus 2 below, you have to at least divide this once. So you'll have something, and then z to the minus 1 on top and z to the minus 2 plus whatever it is below. And then you could go and do the partial fractions. It was the same thing when you were doing the Laplace transform. Okay. So if you have an example like what we had before, this, just backtrack quickly. This expression here, if you multiply this by z to the power minus 3 over z to the power minus 3, you get this. All right. So it is in the negative indices form. It's already factorized for you here, right, in terms of the factors. But if you, I mean, remember one of the things that we said is that if you are uncomfortable with this, you could let something like m equal to z to the minus 1. So that you would, so that this expression here would be 1.4 minus 0.6 m plus 0.2 m squared. Same thing, whatever this was below here. And then you could do the factorizing and then make the substitution back, right? This was like training wheels for using z minus 1. But once you're accustomed, I would prefer that you use the negative index form. All right, so treat z minus 1 as a variable, and then if you do it correctly, you have it in 3 partial fractions now, and you solve for a, b, and c. If you solve for them, you're going to get, in this case, that a was 1.1, b was minus 0.5, and c was 0.83, and so on. I'll leave you to try these. These were actually examples that we did a little over a year ago in Signals as well. You're going to have to at least be proficient enough in this, so you have some time. But when we're doing certain types of filter designs, we start off with a particular type of transfer function, and we're going to have to use partial fractions, all right? And then you go to, after you solve them, you go to the Z transform tables, all right? If the table happens to be, the tables that I give you generally are in the negative form, but just to show you that sometimes you have tables in the positive index form. This and this is the same thing. So if you have it in this form, right, you could either multiply by, if your table is only in positive index, I can multiply this by z over z and get it into this form, or I multiply this by z minus 1 over z minus 1 and get it into the form that we actually prefer. And from that, you know that the expressions, their answer is this one is the z transform of the unit step. This expression, which is like this, is a transform of a exponential function, right? The UN, of course, makes sure that the answer is causal, right? Because UN, as it is, only exists for n from n equal naught forward, okay? And you get the answer here. And you could substitute now. The beauty about this is that I could put in any value of n inside of here to get a value of y and t. So if I put n equal to 75, I will get what y75 looks like, right? You could double check this, just try it by hand as a review and put n equal to 0, 1, and 2 and see if you get the answers that we had before in some previous slides. All right. So you have that. This is just an application. Right. One of the things that why we prefer the negative index is that any number like y, any number like x n minus 1, when you find a z transform of that, n minus 1 has a z minus 1 xz in front of it. N minus 2 would have a z minus 2 xz in it, plus something else as well. All right? So directly related to this, remember, xn minus 1 is a delay of 1. So when you have a sequence and you delay it by some value, z to the power minus whatever that value is tells you the number of the delay, which is why in DSP work and in controls work, we prefer this version instead of the version y z over z. This doesn't tell us the whole story. This does. Minus 1 tells you that there was a delay of minus 1. Minus 2 would tell you that there was a delay of minus 2 and so on. All right? So that's why we prefer to keep the negative index form. All right? So, okay, so this is, there, right. So just sort of quickly to conclude, we're almost there. The frequency response, remember what we said is that to go from the Z domain to the DTFT, we make the substitution Z equal to e to the j omega. So if I have a transfer function in Z and I want to get the frequency response, remember in the S domain, we made the substitution S equal j omega, and then we plot this using Bode plots. In this case, we make the substitution Z equal e to the j omega inside of here. And then you could plot it now for, once you get that, now you're going to get an expression in terms of omega, and you could let omega vary from 0 to pi, and you plot it, the magnitude and the phase, just like we did for the S domain. All right. The power series solution. Okay, we sort of did that already. Oh, this is a repeat here, right? And this was just plotting the points here. You will see this was just to cement what we had, right? And showing you what an infinite response and what a finite response looks like. So this one, this particular one, this is an impulse response that keeps increasing, right? So something like any sort of system that gives you a response like that where it keeps increasing, is not going to work for you. This is going to increase until the value here, well, we just have low amplitude here. But if this is a system powered by 20 volts for argument's sake, then this one is going to crank up until 20 volts and then just stay there. It's going to saturate at 20 volts. That may be good or it may not be good. If there's a motor controller, for instance, it's just going to go up to the maximum speed and stay there. You're not going to be able to control it at all. All right? All right, so a condensed review of things that were done already. And there are 3 separate, actually, like slides with a little more details on this if you need to go back and find the details and so on it. But this was a refresher so that between now and next Monday, when we look a little bit about how to handle transfer functions and so on, I want you to look over those. Well, you could sort of look over this particular presentation here, which I'll upload. And if you're stuck with anything else, go and check back the more detailed descriptions in lectures 11, 12, and 13. Yeah? So, any questions? Comments? We all right? Yeah, there, Andre. I see your hand is raised.
Yeah, morning. So I just have one question regarding the FFT for Wednesday for the test, right?
Yeah.
It was for the BN signal. How exactly did you see it? See the that the that the signal was at 200 bits,
right?
Like what we described.
Okay, if I remember, the question I gave you a particular sampling frequency, right? So if it was just let me stop the recording for the time.